This is Colin Selleck of Binghamton University. This video lecture covers Chapter 13.4 of the book Dynamics by R.C. Hibbeler. Today I will discuss the equation of motion in rectangular coordinates. Today's objectives: you will be able to apply Newton's second law to determine forces and acceleration for particles in rectilinear motion. Activities include applications, the equation of motion in rectangular coordinates, and some problem solving. First, some applications. This man is trying to move a 100-pound crate. How large a force F must he exert to start moving the crate? What factors influence how large this force must be to start moving the crate? Well, I would imagine the coefficient of friction here would make a big difference. You can imagine if he's pushing it on ice or on a sheet of rubber, the answers might be very different. Objects that move in air or other fluids have a drag force acting on them that is a function of the square of the velocity. If the dragster is moving with a known velocity and the magnitude of the opposing drag force is given as a function of velocity, how can we determine the time and distance required for the dragster to come to stop? These problems can be solved using Newton's second law. So the equation of motion is F equals mass times acceleration. It's a vector equation, so I'll denote that by putting a line over the vectors. We use this when the problem requires finding forces, accelerations, velocities, or mass. In rectangular coordinates, we separate the components of the forces and accelerations into x, y, and z. We can also write these as scalar equations. Summation of forces in the x is equal to mass times acceleration in the x, and likewise for the y and z directions. So let's establish a procedure for analysis. It is very important to draw a good free body diagram. First, establish your coordinate system, and then draw the free body diagram showing only external forces. So a word about frictional forces. If something is moving on a surface where there is a coefficient of friction, let's say it's being pulled by a cable of tension T in this direction, always put the frictional force is equal to mu times the normal force, where the normal force is the force here. Let's say you have a spring involved in the problem. The force due to the spring is equal to how much the spring is stretched, which I denote by delta, times the spring constant. The next step is to apply the equations of motion. So in vector form, the equation of motion is seen here, and in Cartesian form it's seen here. The scalar equations can be written from this vector equation. So summation of forces in the x is equal to mass times acceleration in the x. Likewise for y and z. For 2D motion, you only need two equations. The next step is to apply kinematics, chapter 12. Equations of motion are used for forces and acceleration. If you need to find velocities or position, use the kinematic equations from chapter 12. Make sure you use a consistent coordinate frame for both the kinetics and the kinematics. So here's an example. The motor M winds in the cable with a constant acceleration such that the 20-kilogram crate moves a distance s equals 6 meters in 3 seconds starting from rest. The coefficient of friction is 0.3. Find the tension developed in the cable. The plan is, as always, draw a free body diagram, use a kinematic equation, and apply the equations of motion. Sometimes these two are reversed in order. Sometimes you do the equation of motion first, followed by the kinematic equations. It depends upon how the problem is set up. So we'll establish a coordinate system and draw the free body diagram of the crate. Since the crate is on an inclined plane, I'll make my coordinate system along the inclined plane at 30 degrees. The free body diagram, here's the block. We have the tension in the cable, we have the normal force, we have the weight of the crate, and we have the frictional force, which is mu times n. Remember, mu is equal to 0.3. Note that the frictional force is opposite the direction of motion. So since this is constant acceleration, we can use the constant acceleration kinematic equations. We're given distance and the time, and we're asked to calculate the acceleration. So we can use this equation. S is the initial velocity times time plus 1/2 at squared. So the distance is 6 meters. The initial velocity was given as 0 plus 1/2 a, and the time is 3 seconds, so 3 squared. Solve this for a, and you get 1.33 meters per second squared. So now we know the acceleration. We can apply the equations of motion. So here's our free body diagram. So let's sum the forces in the x direction. That is equal to T minus the frictional force, which is 0.3 times n, minus the component of the weight in the x direction, which is 20g times the sine of 30 degrees. That equals the mass, which is 20 kilograms, times the acceleration, which we determined previously to be 1.33. We can sum forces in the y direction. That is equal to n minus the component of the weight in the y direction, so minus 20g times cosine of 30. That equals to the mass times acceleration in the y direction. Now the acceleration in the y direction is 0. So we can solve the second equation for n, 169.9 newtons. Knowing n, we can solve for tension using the first equation. And the tension comes out to be 176 newtons. Here's another problem. The ore car's mass is 400 kilograms. The initial velocity is 2 meters per second. The force in the cable is a function of time. It is equal to 3200 t squared, where t is in second and the force is in newtons. We are on an 815 slope. Find the velocity and the distance when t is equal to 2 seconds. It's our plan. Since both forces and velocity are involved, we need to use both kinematics and the equation of motion. So we'll draw the free body diagram, apply the equation of motion, and using some kinematic equations we'll determine the velocity and distance. So let's draw a free body diagram of the mine car. First we'll establish the coordinate frame. Again, we're going to put it along the slope, and that slope is 8 on 15. So here's the mine car. Its weight, it was 400 kilograms, so its weight is 400 times g. G is acceleration due to gravity, which in this coordinate system is 9.81 meters per second squared. We also have the tension in the cable, and we have the normal force. Now, since the mine car is on wheels, we're going to assume that the frictional force is 0. So this is our free body diagram. Next we'll apply the equation of motion, which is F equal ma, and we'll do it in the x and y directions. For this problem we only need the x direction. So let's sum forces in the x. That is equal to T minus the component of the weight in the x direction, which is 400g times 8 over 17. Remember, the hypotenuse here is 17. So this equals the mass, which is 400 kilograms, times the acceleration. Now we were given that the tension in the cable is 3200 t squared. So we can rewrite this equation as 3200 t squared minus 400g times 8 over 17 is equal to 400a. Solving this equation for a gives you an equation for a as a function of time. So a is equal to 8t squared minus 4.616, and that's meters per second squared. Now we have acceleration as a function of time, so we can use the kinematic equations from chapter 12 to determine the velocity and the distance. So let's write down A again. A is equal to 8t squared minus 4.616 meters per second squared. Now remember that the velocity is the initial velocity plus the integral of 80t. The initial velocity was given as 2 meters per second. So we can write an equation for the velocity is equal to 2 plus the integral from 0 to t of 8t squared minus 4.616 dt. So when you do this, you get an equation for the velocity as a function of time is equal to 2 plus 8 thirds t cubed minus 4.616 t. And when t is equal to 2 seconds, the velocity is equal to 14.1 meters per second. Now we have an equation for velocity as a function of time, so we integrate that to get the distance. So the distance is the initial distance plus the integral of v dt. The initial distance is 0, and we'll integrate from 0 to t, the velocity equation, which is 2 plus 8 thirds t cubed minus 4.616 t dt. You do the integration, you get s as a function of time is equal to 2 times the time plus 8 twelfths t to the 4th power minus 4.616 over 2 times t squared. So when t is equal to 2 seconds, the displacement at 2 seconds is 5.43 meters. This concludes section 13.4, the equations of motion in rectangular coordinates. Next up is 13.5, the equation of motion in normal and tangential coordinates.